Okay, let's go ahead and get started. Any questions before we start? So just kind of a reminder that the homework is due on Tuesday at midnight. If you look at the schedule I filled out, at least the topics I think we'll be covering between now and spring break. So just to give everybody an idea of what we're doing, I moved. The schedule did have graphical models last time, but we didn't get to those, so I moved that to this time. And so starting today and through the end of spring break, or sorry, up until spring break, what we're going to be doing is probabilistic graphical models, which we'll see what those are today, define those. And then the beginning of inference in probabilistic graphical models. And there's two different things that we'll be covering between now and spring break. One thing is, very briefly, is exact inference when you have discrete random variables, and then something called belief propagation and the sum product algorithm, which is an exact inference algorithm. And then we're going to be talking about approximative inference, where you can't do exact inference for either discrete or continuous algorithms, models sometimes. And their approximate inference, the first version that we're going to be doing is from sampling. So something called Monte Carlo method. We're going to spend quite a bit of time, basically, I think like 3 weeks, well, it looks like 2 weeks before spring break. And maybe it'll be a little bit of time after spring break as well. So anyway, we're going to spend quite a bit of time on what's called the Monte Carlo method. And so some of you asked, like in a couple of homeworks we've had, why you have to sample things. We're going to talk about that in more depth. But hopefully in this homework you kind of you start to get the idea that when you have a posterior parameter, when you have a parameter that, when we talk about inference, there's always this parameter that I'm interested in, and I have a whole posterior distribution given my data, and if I can actually look at more than just like a maximum of that posterior. I have a distribution of that posterior. So I can talk about probabilities, I can summarize things about it, and sampling is one of the ways to kind of get a sense of what that distribution looks like. Basically, variability, the uncertainty you have in that parameter beyond just the maximum of the posterior. Okay, so anyway, that's kind of an overview of what we're doing in this next kind of phase of the course. Any questions on that? Yeah, I did put one more link on the reading for next time. It's a set of notes of basically a web page by the same Kevin Murphy guy that you read about the Gaussian conjugate prior to Gaussian. It's another just a web page he has on graphical models, and there's a lot of overlap with the Bishop chapter, but I think it's worth seeing a different perspective, and he's got another example that you can kind of work through with sprinklers and grass and these random variables in a graphical model, and it's useful to go through a few examples and just kind of think about them, actually work out the arithmetic. So in the Bishop chapter, I highly recommend that he's got this example. When we start to talk about conditional independence, he's got this example about, I think it's a fuel gauge and the fuel tank and battery of a car as 3 binary random variables, and then how they interact. And that's a very important example to go through. We're going to talk about that when we get to conditional independence. And then the Murphy notes has a similar example with actually 4 random variables. But when I say go through the example, don't just kind of skim over and say, okay, yeah, whatever. Actually sit down and write down on a blackboard or on a piece of paper, sit down and actually write down the numbers and do the arithmetic. Don't just kind of take Bishop's word for it. Yeah, that's how arithmetic works out. It's all very simple, just addition and multiplication. That's all you have to do. But it's worth actually going through to see why it works that way, because these are very simple things. It's just 3 binary random variables, but it's a very, I think, counterintuitive property we'll get to here of the way these random variables can interact. And unless you actually sit there and do the numbers, kind of the tedious adding and multiplying and everything yourself, you won't really get a good sense for it. So when you're doing this reading, yeah, work through the probabilities, and we'll do a couple examples before. We might even do the Bishop example. Yeah, anyway, but yeah. Okay. Right. So let's see. So today we're starting graphical models. So what is a graphical model? So a graphical model is, in theory, nothing new. It's basically just a way of visualizing a probability distribution, a joint probability distribution over several variables. Okay, so it's actually, everything you know about probability, there's nothing new about probability here. It's just a way to really conceptualize complicated distributions over lots of variables, possibly. Well, as we'll see, even just 3 variables gets kind of interesting. So anyway, but the point is, it's still the basic laws of probability, and nothing new about that. But let's just kind of have an example, and this kind of from the Bishop book. When you have a graphical model, you represent random variables as nodes in a graph. Okay, so we'll draw nodes as circles, and then we'll draw just the name of the random variable as a letter next to the node. So I've got 3 random variables maybe here, A, B, and C. And again, remember, I'm using probability notation by just making A, lowercase a, the name of the random variable, possibly the observation, the name of the observation, and also possibly, we also have it as the parameter side of the probability function P of A. So we'll just kind of use it for all those things. Okay, so yeah, so I have nodes in my graphical model, and if I see a graphical model with 3 nodes, that means I know I have a probability distribution on 3 variables, A, B, and C. I want to point out that A, B, and C could be either discrete or continuous. So this might be a PMF, probably mass function, where it actually tells me the probabilities of certain discrete values, A, B, and C, or it could be a joint density function if it's continuous, in which case I have to integrate this thing to get actual probabilities. So either of those fits into this graphical model situation. For the time being, just to introduce everything, we're going to start out thinking of these things as discrete in some of these examples going forward. But it all holds, everything I'm going to say holds really, except for the examples, this will hold for either discrete or continuous, okay? Then the next thing when you have a graph is you put edges between your nodes and the graph. And the edges in a graphical model, and I'll just draw something like this. The edges in the graphical model don't change this. It's still P of ABC, joint probability, but what they tell you is how you should factor this joint probability. Okay, so we're going to be using, remember, the product rule. So remember, the product rule is just that any joint distribution P of xy can be written as P of x given y times p of y. Right, this is always the case. This product will hold no matter what your joint distribution is. And what the arrows in the edges, and notice they're directed arrows, so this is a directed graph. The directed arrow basically says that I'm going to factor this so that each node is conditioned on its parents. So that the arrows going into this node are its parents. So I've got A and B are parents of C. And that means I'm going to write P of C given A and B. I'm always going to write a node given its parents in my factorization. Okay? Now B has one parent, so it's going to be P of B given A. And A has no parents, so there's not going to be anything in the conditional there, it's just P of A. Okay? And you can kind of verify that this actually is a proper factorization of this joint distribution. It's just using the product rule a couple of times, right? If I multiply this by this, I get the joint P of A and B, right? This is P of A and B, and then A and B factored together with that gives me A, B, C together. Okay? I mean, I could point out that this simple product rule is just the graph x. Let's see, x given y, so it's going to be that graph, right? If I flip this, y given x, and then this p of x, the arrow just flips. Okay, so, yeah.
So graphical model is always a directed graph?
No. There's two types of graphical models, one that's directed and one that's undirected. We'll talk about undirected, let's see, today's Thursday, yeah, next week. Yeah. So undirected, if you jump ahead in the Bishop book, today we're covering roughly 8.1 and 8.2, but we're at 8.3. He's talking about Markov Chain fields. That's just another name for an undirected graph. So these are sometimes called Bayesian networks. Or Bayes nets, but it's just a directed graph version of probabilistic models. The name Bayesian here doesn't have to be Bayesian. There's nothing Bayesian about factoring a joint distribution, so it doesn't technically have to be Bayesian. It's just when we're doing these things, they're usually Bayesian models. So this word may or may not be appropriate. Okay, so that's the basics, and that's basically all we're doing with graphical models, is drawing our random variables as nodes in a graph, and then writing down a factorization of the joint distribution in terms of the edges in the graph. Okay, and again, this isn't really, if I just have a joint distribution ABC, any factorization of ABC is a valid, probability representation P of ABC, and it could be equivalent. The probability model, joint model could be equivalent, and I just redraw the graph, and it's the same thing. Okay, but what we're going to see is that how you draw this graph, you can actually specify your model in terms of, instead of specifying the entire joint distribution, I now need to specify these three conditional distributions. Or this one's just a marginal, these two conditionals. Okay, so how you specify your model changes, how you really think about this joint distribution. Even though you could specify it in a different way with a different graph, specifying it this way, and we'll see the examples, changes how you think about it and how many parameters you need to specify these types of things. And the bottom line that we'll point point I'll make here with some real examples is the goal here is what we want to be able to do is make large, complicated models, lots of variables, lots of parameters, but we want to make them as simple as possible, okay? And if I just say model the entire joint distribution of lots and lots of variables, as we're going to see in a minute, that can be very expensive in terms of the number of parameters you need, whereas if I break it down into simpler pieces, I can reduce the number of parameters, I can reduce the complexity of the model, but still model the same number of random variables that I need to represent my data. So that's kind of the goal, one of the goals I should say of the graphical model is thinking of things that way, breaking down complex things into simpler pieces. And as we've talked about so far in class, we've done basically single univariate distributions with one-dimensional priors, and the most complicated we did with univariate distribution with 2 parameters with priors. That was the multi-parameter Gaussian. You can think of, I can put these together, so I have random variables. I can put these together, the distributions that we've already covered, into as kind of building blocks for these conditional distributions, and build more complex models from the simple ones we've already done. So that's another way to think of this graphical model stuff. And then the final thing, benefit of why do we do these graphical models, is that when you have this complex model, if you can draw it and look at it visually, rather than just specifying, like this is a normal distribution, this is a Bernoulli, this is a yada, yada, yada. You can actually draw it. You can see how the different random variables interact. And we're going to see in just a minute, you can start to actually find very somewhat interesting independence properties between random variables just from looking at the graph that you draw. Okay, so understanding how your model in some sense behaves, how variables interact, is easier if you draw this graphical representation as well, as we'll see. So those are kind of the main reasons we do these graphical models. Okay, any questions about that so far? It's just the basic definition. Okay, the other rule that's going to be important in graphical models, of course, the product rule is just how we put these things together. Actually, there's, I think, maybe 3 rules that are going to be important. The next, I should say, the next rule that's important is, we usually call it the sum rule here. I guess it's an integral rule when you're doing continuous, but we'll call it the sum rule for discrete. And that is basically just how do I marginalize out one of the random variables. So if I have this p of xy graphical model here, the sum rule says that if you want p of x, you have to sum over all the possible y outcomes. And again, I'm using this kind of shorthand that just means, this means sum over all the possible y's. That could be a finite or infinite sum, just whatever. I have to sum over the y's, and if it's written this way, I can expand that out in the conditional version. But that's kind of another piece that we're going to need. That's just marginalization. So this comes up a lot in graphical models. So just as a reminder, that's how you get p of x. And then the final thing that will come up, which of course we also know, is I can reverse these arrows by using Bayes' rule. So I can always take an arrow and flip it if I use Bayes' rule, right? So if I have a model that has y arrow pointing to x, and I really want the posterior, if you will, p of y given x, then I just use Bayes' rule, where this is what I've specified in my graphical model, and then the denominator I get using the sum rule, p of x, and that lets me take that arrow and flip it, whoops, flip it around the other way. Okay, so these are kind of the three, and again, these are just simple, probability 101 rules that we did like in the first day, just as review. But these are the only three rules you really kind of need to know, and Basil is just kind of combining the first two rules. The only rules you need to know to kind of manipulate everything we're going to do with these graphical models. And again, this is either discrete or continuous. The only difference is the only thing we have to change is to be an integral over y, right? If y was continuous. So we'll see you can actually have graphs which are all continuous, all discrete. You can also have graphs that are a mixture of some variables are discrete, some variables are continuous. Yeah. Okay. Okay, so yeah, so talking about discrete random variables, I think it's useful to think of just binary random variables to start out here, just to get a sense for why these graphical models could be useful. Okay, so one thing you'll find is that this lecture will seem like it's very trivial, like there's not anything, like I said, there's not anything new going on here, but I think hopefully it'll become apparent, maybe even by the end of this lecture and into next week, that this is actually a really powerful framework. So it's gonna seem like we're just doing very simple, product rule, sum rule, base rules, just simple manipulations that we all know very well. Nothing complicated like the kind of derivations and conjugate priors from last time, but you're going to see that this builds up to actually a really powerful kind of conceptual framework for doing probabilistic models. Okay. So yeah, this might be a breath of fresh air from some of the mathematical lectures that I have. So yeah, so let's take a look at just binary random variables. So if I gave you let's say n binary random variables. So these are like just marginally they're Bernoulli, but jointly they could have interactions and correlations with each other. So but if I just gave you n binary random variables, and I think about the joint distribution for all these binary random variables, then who can tell me how many parameters do I need to specify this full joint random, this full joint distribution, x1 to xn? So how many? Let me start this way. How many different distinct values can the sequence x1 through xn take if they're all 0 or 1?
To the end?
Yeah, 2 to the n, right? I know I've got computer scientists in the crowd, so over binary numbers. Yeah, so this is just an n-length binary string, right? So it's 2 to the n, because each one is 2 numbers, and that just multiply them all together, I get 2 to the n sequences of 0, 1 kind of bit string here, right? Okay. So there are 2 to the n outcomes possible. And remember, if I want to specify a probability on a discrete outcome, I need to know the probability of each outcome. I need to specify the probability of each outcome with one constraint, that all the probabilities sum to 1, right? So if I tell you the probabilities of the first 2 to the n minus 1 outcomes, oops, 2 to the capital N here, 2 to the n minus 1 outcomes, I tell you those probabilities, then the 2 to the nth, the last one is fully specified to make it add up to 1. Okay, so there are 2 to the n minus 1 parameters to specify this distribution. Okay, I have to give you 2 to the n minus 1 numbers. That's similar to something less than 1, but that's not a constraint that loses any degrees of freedom there. So this is a lot of parameters, right? There's an it's exponential in the number of variables I have. So to specify in general, a binary set of n binary variables, it's exponential in n. And as you can imagine, I chose binary, but we could have done anything about it. If 2 was replaced with k, like if these were 3 categorical variable, 3 outcomes or 4 outcomes or 5 outcomes, whatever, I would have k to the n. So this is binary is the simplest case, but it obviously holds for any type of discrete variable. Okay, so that's very expensive, right? Now, if this were to factor as p of x1 times p of x2 dot 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 p of xn, in other words, if each of these binary variables were independent of each other, now how many parameters do I need? So for just one of these, I need how many? One, right? Because I just need p, or the theta, right, in Bernoulli gives me 1 minus theta for a 0, theta for a 1. So I just need the theta for each one. So I really just need n. So here, if they're independent, then I just need n parameters. That's much easier, right? That's linear in the number of variables. This is O of n, this is O of 2n, 2 to the n, and so this is exponential, this is linear. So independence, if we think about, if I'm going to do inference on a set of n binary random variables, I'm trying to infer what the probabilities are. If I don't make any assumptions about how those variables interact with each other, I've got a really nasty dimensionality of the things I need the complexity of the things I need to estimate now. If I make a very simplifying assumption, the most simplifying assumption I can make, other than fixing some of these guys, if I make the most simplification I can, I get down to just n parameters. Okay, so that tells us that I can reduce the complexity of my problem by assuming some independencies in my random variables. So this graphical model, the fully independent x's, is the model that just has these random variables, let's say n is 4 here, with no edges, right? If I have no edges, then this factorization says everybody's conditioned on their parents. If nobody has any parents, everybody's conditioned with nothing. And so I would get something like this. All right? So the best graphical model you can have, if you're just in the simplest case, n binary random variables, is a graphical model with no edges. That is your best case scenario in terms of the easiest to solve. It reduces you down to just n parameters instead of 2 to the n minus 1 parameters. Okay? And of course, as you can imagine, as I start to add edges, I go from this easy case, and I can get all the way to this case if I get a graph with kind of the worst case scenario number of edges. So the first thing we might take a look at is, can I actually get a graph always? Yes, question?
What is a Markov chain?
Yeah, we'll do so Markov chain, so I'll get that in just a second. A Markov chain would be, my chain's got kind of a kink in it, but the point is it would just be a string. And so everybody has, so there's one person who has, one variable that has no parents, and then everybody else has one parent, is a Markov chain. So it's when they're basically ordered in a line, which is one edge between two. Yeah. So this is a Markov chain, which is a very important graph. We're going to do Markov chains ad nauseum between now and spring break. Okay. So yeah, so actually let's take a look at the Markov chain. So how many parameters do I need? Before we get to, let's say how many parameters I need for the Markov chain, how many parameters do I need to specify one of these conditional distributions when they're binary? So if I have like this one, P of x3 given x2, what does this mean exactly? Both of these variables can take on two values, 0 and 1. But how many things do I need to specify? So there's really kind of 4 different things here, because I've got 0, 1 here, 0, 1 here, and all the combinations is going to be 4. But how many, I don't really need 4 parameters. How many parameters do I need in this case to specify this?
2.
Yeah, 2. And why is that?
x3 is on x3, x2 is on x2.
Right. So if I set x2 to 0, then I need to specify what is the probability of x3 equaling 1. And then I know what the probability of x3 being 0 given. So let me write that out more carefully, because this is the critical point. This can be written as a table where I tell you what is x3, either 0 or 1, and then I tell you, let's see, the probability of, I tell you x2, the probability of x3 given x2. I need to tell you x2 and x3. No, I don't need to tell x3. Sorry, I have this. This is the probability of x3 equaling 1 given the value of x2. So, yeah, sorry. Messing that up. So I just need to tell you the probability of x3, these two values, x3 equal to 1, given x2 being this value or this value. Because once I tell you this value, the complement P of x3 equal to 0, because the conditional thing is, if I fix x2, the conditional thing is still a probability, so it's just 1 minus this to get the probability of 0, right? And so we'll see, you'll see in kind of like in the Murphy example on the web that I've linked to, which I recommend checking out after this lecture. We write these things in tables like this. You write down the probabilities. If I had, for instance, something more complicated, let's say I had this picture, x2 and x1 in the conditional, that's where I need a more complicated table. I would need x1 here, and I would have to have 0, 0. I really have to have 4, so 0, 1, 1, 1. Right, so that space there, but yeah, that's the, you would then have to have all possible combinations of the things in the conditional, but then you just need, for each row in this table, you just need the probability of this being a 1, given whatever configuration of the conditional. Okay, so the general, that's a little messy, but the general, if I write this as P of y given x1 through xk, this type of conditional probability, if I have k parents, then I need 2 to the k parameters to specify this type of conditional distribution. Okay? So, yeah, question?
So probability of x3 equals to 0 given x1 and x2. will be the complement of x3 equals to 1 given x1, x2? No.
Wait,
So we specify for every row.
if you specify, for instance, x1 equal to 0, x2 equal to 0, and then I tell you, let's write that down. Yeah, so if I tell you what is probability of x3 equal to 1 given x1, x1 equals 0 and x2 equals 0, this is equal to 1 minus the probability that x3 equals 0 given x1 equals 0, x2 equals 0. That was mine. So each row, I fix the things in the conditional, then the complement rule still holds for the thing that's on the left-hand side of the conditional, if that makes sense. So conditional probabilities are really, when you fix the condition, you can kind of just think of it as just the same rules that probability hold for the thing on the left side of the conditional. So that's what we're doing there. So that's why each row is basically fixing the conditional, and then I've got just one parameter to specify the binary thing that's left on the left side in this picture. So you have to build a table that goes through all possible outcomes for the things in the conditional, is the point. So what we can see now is that the fewer parents that nodes have, that's why the Markov chain is nice, because everybody has at most one parent. But the fewer parents I have, because k parents results in 2 to the k, I'm going to keep k as small as possible. So I kind of want to reduce edges, but I specifically want to reduce nodes getting lots of parents. So, I mean, if I distribute my edges around so that I have minimal number of parents as possible, that's a good strategy. So the chain is nice because it doesn't have many parents. So now coming back to the chain, now that we've seen what conditional distributions, how much they cost in parameters, how many parameters do I need to specify this chain? Total, if I have four things in a chain.
2 times n minus 1.
2 times n minus 1, not quite. That would be 7.
No, minus 1. 2 times. So it would be 6.
Oh, 2 times,
Yeah.
in parentheses, n minus 1, 6. No, I think it's fewer than that. It's slightly fewer, if that's a good hint. Yeah. So how many do I need to specify x1? It has no parents. 1. I need 1. Okay. How many do I need to specify x2? 2. Oh no, sorry. Wait.
It would be a ring.
No. Yeah, that's right. 2. Yeah. Sorry, I was wrong. It's slightly more. Yeah, than 6. Yeah. So then, and x3 and x4 are the same as x2, right? I need 2 here and 2 here. Okay. So total, add that up, I get 2, 4, 6, 7. So 7 parameters. How many would I need for a full joint distribution of 4 variables? Here's 2 to the 4 minus 1, right? Yeah, 16 minus 1, so I need 15. So I basically have cut my parameters down in half with this particular example. Now, in general, kind of your 2 to the n minus 1 plus 1 is basically the general formula. So in general, if I have a Markov chain, I'm getting really messy with my this side of the board. So in general, though, a Markov chain, so Markov chain requires 2 times n minus 1 plus 1 parameters. Okay? Because I need 2 for everybody that has a parent. The first guy doesn't have a parent, and he just needs 1 because he's just a Bernoulli by himself. right? So I get this for everybody with a parent and this for the first one. So notice a Markov chain, I don't have an independence assumption. And in fact, you know, this tells me that x2 depends on x1, and really x4 also depends on n1, but kind of indirectly if I go down the chain. I really get dependency across everybody, but I still am linear in the number of parameters I get. But there's a factor of 2, so it's like twice as much roughly from if I get perfectly independent. Okay, so you can kind of see how keeping the graph simple lets me get away from this exponential growth of number of parameters here. The last thing in terms of this kind of number counting, I want to make an argument that I can always get a graph that will give me this kind of maximal number. Yeah, question?
The simplest of cases, the independent case, we have n minus 1 parameters.
No, I think you still have n. You have to specify a p or a theta for each one's a Bernoulli by itself. You have to specify that theta for each one of those p of xi's.
If you got some of the
No, they will still sum up to 1.
non-specified the last one.
Yeah, no, you can specify all of them. What has to sum up to 1 is, yeah, this n, you know, n sum over everybody, right? And because each one sums up to 1, you can factor it out into a sum all by itself. It sums up to 1. You can sum up each one by. So think about the sum over x1, you know, x2, xn. You know, if I just sum the x1 up by itself first, it sums up to 1. And then I do the next sum, it sums up to 1. You keep cascading that sum, so everybody keeps summing up to 1, the whole thing sums up to 1. Yeah. Sorry, this is not equally unless I can write the sum over there, obviously, but yeah. Okay, does that make sense? Yeah, so if I specify, no matter how I specify these Bernoullis, they'll be guaranteed to sum up to 1 if I specify correct Bernoullis for each one. And same thing with no matter how I write this graph, with one caveat, there's one rule I have to follow here, we'll see in a minute. But if I write a valid graph here, and I give you any table like I just drew there for condition, as long as the conditional probability is a valid conditional probability that sums up to 1, as long as I specify each conditional probability correctly, the whole joint probability is probably fine. It will sum up to 1. Sometimes we'll see that you can write these tables that are unnormalized, so they don't sum up to 1. And that's fine because you can just kind of say that it has to normalize. I'll not worry about the constant, what it normalizes to, until I've finished. When we get to these inference algorithms next week, we'll see that we can kind of leave that normalization out usually. Okay. Right, so yeah, so I want to make an argument that I can always get this, a graph that'll give me this complicated thing here. So if I take that graph right there, how many parameters does it need? So we've got 2 parents, so how many parameters does that mean this guy has? 4, right? 2 to the k, where k is 2, is going to be 4. This guy has 1 parent, so he has 2 parameters. And again, this guy has no, but you always have to have 1 parameter for Bernoulli by itself. So here I add this up, I get 7 parameters. And what is the kind of max? It's also 7. So 2 to the 3 is 8, minus 1 is 7. So this one has the maximum number of parameters already. So this graph didn't help me save me effort. Right? Which is maybe fine, like it's not the only point of graphical models is to reduce the number of parameters, so sometimes you have, you know, a lot of parameters. Okay. But yeah, but I can kind of extend that example. if you think about going to 4 nodes, I'm going to make one node take the other 3 as parents. I'm going to take the next node that have the other 2 that are left as parents. We're going to see that I can't make this guy both a parent and a child to each other. So there's a kind of like an incest rule. You can't be parents and childs of each other type thing. And so then I've got this one guy left that I can make a parent here. And if you count this up, I get 2 to the 3 or 8, 2 to the 2 or 4, 2 and 1. You add this up and I get the 15, which is the max for 4 that we got there, right? And this trick works no matter how you do it. With n nodes, I always take the one node gets n-1 parents, another node will get n-2 parents, so forth and so on. So I get basically the sum of, let's say, j equals 0 to n-1 of 2 to j is the number of parameters total. If you think about it, I can always do that with n nodes. Then, and if you look at your geometric series, you can see that this will reduce to the n-1. So that type of graph will always give you kind of the maximum number of parameters. So you can always get the maximum number of parameters out of n nodes with this graphical representation. Okay, I think that's enough parameter counting exercises. Any questions about that? That's okay. Oh yeah, so I made a comment that you can't have this node be a parent of its own parent. So you can't have arrows going this way. Why is that the case? So far we've said that a graphical model is just a directed graph of random variables that represents conditional probabilities. There's one rule that you have to have. That directed graph has to be acyclic. So it's a DAG, it's a directed acyclic graph. You can't have cycles, loops in the graph where you start at some node, you go through the directed arrows, and you come back to that node again. So why can't I have loops? So if you think about just one random variable, the following graph doesn't make any sense, right? Because this is p of x given x, that is really nonsense. That's just like 1, I guess, always. So then this isn't really, you can't specify that to be the conditional distribution because then that kind of invalidates this guy as a random variable in some sense. Or you can just say that this is nonsense. That's really the right way to think of it. So I clearly can't have a cycle just with a node of itself. So then let's think about if I have 2 nodes and I had this picture. What this would say is that p of x1 joined with p of x2 factors as p of x1 given x2 times p of x2 given x1. And this is just not an actual rule of probability. That's not true. You can't. The other way to think of it is you always have to have somebody, has to be a marginal distribution, really, there has to be somebody that has no parents. Otherwise, you're not starting, there has to be somebody that has nothing on the right side of the condition. It might be a joint thing with no condition, but something has to, question?
So I remember the Markov chain, which has a loop to itself, like we'll see.
No, the Markov chain, no, there's no loop. So it starts at x1 and it goes to x4, and then there's nobody leaving x4, so there's no coming back.
Something the Markov model, I think that is kind of, that is for states, right?
Yeah, there's like a finite state machine, that finite state machines can have loops. But so we have to be careful. These are not finite state machines. So a hidden Markov model, which maybe we'll cover that actually just as an interesting model. A hidden Markov model combines a finite state machine with a Markov chain. So the hidden part is you're in this hidden state, and that hidden state has a state machine transition, and the transitions of that state machine can have loops and everything. But yeah, that's a good point to bring up. So to make a distinction that this is different from state machines. State machine technically isn't, so you might see state machines like I have a state 1, state 2 type thing, and I have a transition matrix, which is like a probability of going from state 1 to state 2, going from state 1 and staying in state 1, and going from state 2 staying in state 2. So you'll see pictures like this, right? You might have 3 states, 4 states, or whatever. But these are actually outcomes, not random variables. So this graph means something completely different from a graphical model here, because here I might have a random variable x, and the random variable x will be either equal. Its outcome will be either it's in state 1 or it's in state 2. So these are really the outcomes of the random variable when you see a state machine like in a hidden Markov model that has loops in it. So that's actually a good thing if you've seen these before, if you've run into them, and maybe we'll talk about them as an example. But yeah, these are actually talking about the states. These are talking about the random variables themselves. So X could be a node, but the S's wouldn't be nodes. Yeah. But this is probabilistic because you have probabilities of moving along each of these arrows into different states, and so that governs the probability of X being in either state 1 or state 2. So yeah, maybe we'll talk about that actually. But it is at this juncture, just think that these are different things, and loops in our case are not allowed. Okay. So yeah, so I can't do this either. I can't go x1 back to x2. I can't be a parent of my own parents. Okay. Right. I guess there's no way incest can make you parents of your own parents. That's just not possible. Okay. So anyway, so maybe incest is the wrong word. So this is also not possible. But now the real question is the general case. I'm claiming that you can't go from x1. X2 xn, and then back to x1. You can't have a general loop in your graph anywhere. Okay. Now, how do we see that? I'm not going to give a formal proof, but just to give you the basic argument. Anytime I have somebody in the middle of a chain here, I can always integrate this guy out with some rule. Okay, so if I multiply this conditional distribution of x2 given x1 and everything together, and then just sum over x2, if this were a probability distribution, I could basically pull this node out, marginalize it out. Okay, and then I would have the chain x1 to x3 to x n minus 5. That x2 would basically pop out, and I would just have a shorter chain like so. Eventually, if I keep marginalizing these nodes out, I would get down to this case, and I would have this conflict again. Yes.
I don't understand what you mean by marginalizing out.
Okay, let's do it with this short chain as an example. So let's say I have x1, x2. Yeah, it's worth going through this slowly so that everybody understands. Yeah. So what is this? This is just a Markov chain, like 3, and this is telling me that my PBF or PMF, I guess is what we're just reading for the time being. P of x1, x2, x3 is equal to P of x1 times P of x2 given x1 times P of x. leaving E given x2. Okay? Now what I want to do is I want to get rid of x2 in this graph. Okay? And so what I want the joint distribution of x1 and x3. And so what I have to do is sum over x2. This will give me x1 and x3. Right, that's equal to that. So let's go to sum over here also. This thing, let me erase this because I'm starting to get equal signs in different directions. This thing is equal to what? I can bring,
The second one goes away.
yeah, x3.
That's x2.
Oh, sorry, x2, yeah, thanks. I can bring x2 inside here. Right, is everybody happy with that? I can bring that inside with x1 there. And I've got x2 here. I use the product rule to put these two together. x2, oh wait, no, I can't use the product rule. But, hang on. I think I needed to use the product rule first. No, I can't. Yeah, I can use the product rule here. Okay, good. Yeah, sorry, I was right. So I'm going to use the product rule here to get the joint x2 and x3 given x1. Right, everybody happy with that? I'm using the product rule between these two conditional distributions. And then marginalizing the x2 here leaves me with just the x3, which is p of x1 times p of x3 given x1. Is everybody happy with that? And then this resulting thing tells me, because again, this marginalization of the full joint was really to get rid of the x2, and that is equal to that. So that tells me that this joint between x1 and x3 factors like so, and that is x1 has, sorry, x3 has one parent, which is x1. Like that. So if you have a chain, you can always delete a link in the chain by marginalizing it out, and when you delete that link, I deleted this x2 link, the chain's still there, it just jumps to the next one, so you get x1 to x3. Yeah.
How did you combine those two? It seems like the product will work out between p of x3 given x2 and x1.
Yeah, so that's right. Yeah, so this, what we're saying here is that, okay, this is all jumping ahead of, this is conditional independence. And we'll have, yeah, this is what we were going to talk about next, actually. So yeah, I realized kind of mid derivation here that we're kind of jumping ahead of what we haven't really talked about yet. But what I'm using is the fact that that thing that you're talking about here, p of x2, or sorry, x3 given x2, x1, which you're right, to do the product rule here, I really need an x1 here, but this is actually equal to x3 given x2 without the
Because there is
x1.
no direct dependence. That's one of the escape.
What this statement says is that if I know x2, then I know the probability of x3, right? And I don't need to know x1. Conditioning on x1 doesn't change that. So if you actually observe the value of x2, because you directly have this conditional distribution, so we can kind of say this without talking about conditional independence right now. If I observe x2, I know this conditional distribution, so I know directly the probability of x3, and knowing x1 doesn't change that probability. Now, if I don't know x1, sorry, if I don't know x2, then x1 does influence x3. This is what this says. Because this is saying if I don't know x2, I didn't grade it out, in other words, then x3 and x1 are related. But in this first graph, observing x2 means x1 is irrelevant to what x3 is. This is the first version of conditional independence. This is this equation here is what's called conditional independence of x3 and x1 given x2. So, right, we're gonna cover that a little more carefully. Okay, but does everybody buy this argument now that I can delete a link in the chain? And because I can delete a link in the chain, any loop that you see in a graph with enough marginalizations to simplify it down would lead you to this being actually in the graph, which is not good. Because that, I hope everyone agrees, is not a real probability that's valid.
Well, can you delete a node from any graph? It doesn't necessarily need to be a chain.
Yeah, so if I use the sum rule on the product of every conditional distribution in a graph, the product of all the conditional distributions in the graph gives me the full joint distribution. And then I can sum over any random variable you want. So I can delete any node in the graph. Now, how that changes the edges can be complicated. In a chain, it's somewhat easy. The chain just kind of jumps over the deleted node, yeah. But yeah, so I mean, we could work it out, but I mean, we could go. I mean, yeah, and actually, I recommend, because you can sit here and watch me do stuff on the board, but I recommend play with a few graphs. You know, there's the example in the book, and then the web page that has actual numbers behind them. Play with some graphs. Figure out what would happen if you marginalized a node, did whatever, did Bayes rule, whatever. And I think if you got some experience, just actually doing this yourself, it helps you kind of understand things. Okay, let's see. A couple of points I wanted to make. Oh yeah, so the next point I want to make is why would we have models like this with direct edges? So one of the reasons we talk about these Bayesian networks with directed edges is because we want to write things that are generative models. And what do we mean by generative model? Now, basically, one of these directed graphs doesn't have to be generative, but we're going to talk a lot about generative models. And one way to think of a generative model is that if you sample from it, you basically generate the data that you observed, okay, or something like the data that you observed. So that's kind of the very vague definition of a generative model, is that I can, if I put together these probability distributions and I just sample from them, I sample random values from them, then they would generate something that looks like my data, okay? So Bishop in the book had an example, like if they're doing a computer vision model, this is a very simplistic example, these obviously couldn't be binary variables, but your data are images of some object in the world. Let's say that's your data is an image. And what would a generative model of that be? Well, you've got maybe some very complicated representation of an object, like, I don't know, a car or an airplane or whatever, and that is somehow a random variable. You've got kind of the camera or the position of the object, and you've maybe got, I don't remember exactly what his example was, you've got maybe lighting and so forth. Anyway, if you could somehow randomly generate all these things and somehow represent them in, obviously that's not an easy task, this is, like I said, these aren't binary random variables, then these things, you might have some way to then generate an image from these kind of things. And that is kind of what you do in like ray tracing. You generate an image. So you can think of computer graphics is the generative model for computer vision is the inference model that goes back the other way. Where anyway, yeah. So anyway, the idea behind generative models is that I need to give you a model that's complex enough to generate realistic data. Okay? Now, depending on what kind of data you have, that can be a really easy problem or maybe a really hard problem. So if I gave you just, again, like numbers that were like heights of people, then you could say, well, I'm going to treat that as like a Gaussian variable, and I just need to know what the mean and the standard deviation is of people's heights, and then I can generate things that look like heights, probably. So it can be very simple, or if you said, I want to generate things that look like images of real people, that's a very hard generative model to do. Computer graphics doesn't really have real people nailed down, probably. They're getting close, but maybe not perfect. So anyway, that's one reason to have arrows. Okay, the arrows say, because if I want to sample from a graphical model, I can't sample directly images because I need to know, I only know their conditional distribution given these things. But what I can sample is I first sample what the random object is, I then sample its random position, and then I sample maybe random lighting, and then I can put all those together to get an image. So generative model tells you what order to sample things in to generate the final thing at the bottom of your graphical model that has no output to it, if you will. Okay, so that's kind of, we think of these arrows as representing how data was somehow generated. That's kind of one way to think of these arrows. Okay? Another thing that comes up is the notion of causality. And we have to be a little bit careful when we're talking about causality. Technically, probability can tell you nothing about causality. Okay? Probability, can tell you P of X, but it can't tell P of Y and maybe a conditional probability of P of X given Y or so forth and so on, but it can't tell you did Y cause X to happen, if you will. But we can use logic to decide whether causality is an appropriate thing in the model, okay? And this is really more, again, it's not really in the model, but it's our way of thinking about the model. So if we go back to our example from the first day of class, a cold and a runny nose, binary variables. If you have a cold and a runny nose, well, the cold causes the runny nose, not the other way around. It's not like I get a runny nose and that causes me to get a cold. If I get a cold and that bug in me causes me to get a runny nose, right? So this is, the arrow here represents causality. You want arrows that go in the direction of causality. So the thing that's apparent is causing the child. Okay. So I have some chance to get a cold, and then given that cold, that gives me some chance of getting, pretty high chance usually, of having a runny nose along with it. So I was going to do this example in class, but I think maybe I'll leave it as an exercise since we have just 10 minutes left. If you go back to the cold example from the slides in the very first lecture, the probability crash course review, think about if I did this graphical model, how would I specify the probabilities? So write down the tables. So remember the slides, what we did was we had the full joint cold and runny nose, 0, 1, 0, 1, and we had, this 2x2 table with all the joint probabilities. So this was P of RC, joint table. And now the question is, what's P of C and P of R given C? How do I write that as a kind of two pieces of information here? So you might try that and play around with Bayes rule and sum rule for just this very simple graph. I really recommend doing the three-way graph that going through that carefully in the Bishop book. Maybe we'll do that one in class as a more complicated example. But just as like a warm-up to that, you might just try the very, very simplest case to look at this graph. Okay. Let's see. Right, so we covered DAG part here. Oh yeah, the last thing I want to say about the DAG. So this tells us that a graphical model has to be a DAG. It has to be acyclic, directed acyclic graph. But the other thing that I'm not going to give you proof for, but you can kind of hopefully convince yourself, is that any DAG is a valid factorization of a probability. So DAGs are equivalent to Bayes nets. So what I mean by that is we've seen that any Bayes net I give you has to be a DAG. And I'm telling you, any DAG I give you can be interpreted as a valid Bayesian network. Okay, so try to convince yourself of the implication the other way. It's if and only if is what I'm saying here. Okay? But yeah, we won't. It's simple to, hopefully simple to see. But okay. Okay, so so there's a couple other pieces of notation that we'll just end on here and pick up next time. So beyond just having nodes and edges, there's more to probability distributions, right? So we have parameters to those probability distributions. So like for Bernoulli, we've got a theta parameter. And there's one other distinction, is that we typically have data, which is observed random variable, and then we have parameters which are hidden or unobserved variables, random variables. And so for instance, in the cold situation here, we don't directly observe, do you have whatever bacteria or virus or whatever it is that causes a cold. I mean, that's a really vague thing, but whatever, we don't observe that directly. We observe the running nodes. And so this would be observed, and this would be hidden. And what we do in a graphical model, in the pictures, to make sure this information is all in the graph, we shade or fill in the nodes that are observed and leave the nodes that are unobserved as just empty circles. Okay, so this will be a picture we see a lot of, a filled-in node and one apparent hidden node. Basically, what we've done so far in class looks like this. We've done where I've got P of X given theta likelihood, and I've got P of theta prior. And that's basically, you can think of this as Bernoulli given the theta parameter, or Gaussian given the mean, all these different things we've done. The one parameter models, they are basically a graphical model that looks like this. Right? The next piece of notation, and if we stick to the Bernoulli, this would be helpful. So if I say x given theta is Bernoulli with parameter theta, and then my prior theta, for instance, it could be uniform, and then it has no parameters. We did that one first. But let's say I have a beta distribution that had two parameters, alpha and beta. So you can put these parameters into your graphical model also. They basically look like a dot. Okay, so that's a parameter. And you can either do something like, alpha and beta together, or if you want to get complicated, you can make it two dots. Just say alpha and beta are parameters to the distribution theta there. Now, of course, when we're talking about Bayesian, depending on your preference, you can either call this the parameter, or this is a random variable. These are parameters. If this is the parameter, then we'll typically call these guys hyperparameters. Again, depends on your what you want to call them. if you start getting stacks of parameters, priors on top of priors, you might have hyper parameters, I don't know. But anyway, the most important distinction though is that this is an observed random variable, this is an unobserved random variable, and these are constants. You think of it that way. Whether you call them parameters or hyperparameters, which how you make that distinction is kind of sometimes arbitrary. Okay, so yeah, so basically our models look something like this. Now, one last piece of, last piece of notation, this x, we really don't have one data point, so we don't have one random variable. Remember, if I have a random sample, each data point has a random variable associated with it. So I really have x1, x2, out to xn, and they all have arrows to them. Okay, so this is really our Bernoulli example in full graphical model form. So it starts to get a little more complicated that way. But one more piece of notation that simplifies this graphical model is called plate notation. And that basically says anytime you have a repeated graph, each of these arrows here are all really the same thing. So I'm going to take this repeated n times, and I'm going to just compress it down to 1, because it's just the same thing n times. So I draw this same graph. Again, I've got alpha and beta as parameters. And my x's will have an eye on them. And I put a plate around that. And in the corner of the plate, I just say that gets repeated n times. And that's equivalent to this. I shouldn't do this. This looks like a plate. That's not a plate. Okay? So plate notation just lets you, especially for your data at the end, you usually have lots of instances of data, and so you want to repeat, n data points. So you draw a plate around it instead. Drawing n points. Okay. I think that's a good stopping point, and we're out of time. Any last questions? Anything? We'll pick up here on Tuesday.